Good afternoon. So my name is Azhar Lalani, and I'm joined with my colleague Emilio Mistretta, and we're from the Smart Systems Research team at the University of Hertfordshire. Today we'll be giving three presentations. The first is a Knowledge for Business program project that was undertaken at Building 16 in BRE Watford. And the second and third presentations are our individual research topics for our PhDs. So for the Building Research Building 16 project, Knowledge for Business, we were asked to review and improve on work that had been previously carried out. Building 16 was the first energy efficient office of the future, and it's very efficient for energy and thermal properties. So we were asked to investigate and implement real-time power management solution and device priority based on low carbon utilization within the building. We had to use existing hardware that was previously bought beforehand to continue this project, which I'll list in the next slide. And the control system will be based on the demands of how much solar power we're able to capture, the demand of how much the system requires, how much energy is being sent back to the grid from the solar, and how much distributed storage we're able to capture by that. And to actually showcase how this system will work, we'll be developing the actual control system. And to show the project viability, we'll be actually showing you later on in the slides a USB charging box that was used for the distributed storage. So here's an overall diagram where we were to start from in the beginning. We had two PV arrays connected to an inverter, three energy meters, which we were able to connect to via the internet, and a power over Ethernet switch, which was able to send power to three PCs at this time. So here's a little bit more details on the actual system. The PVs consisted of 1.5 kilowatt arrays, Sunny Boy inverter, three Carlo Gavazzi professional meters, power DSI and power over Ethernet injector, and the serial to Ethernet converter.
So as my colleague Al just mentioned, we have a PoE injector which actually provides power to ports. So we were able to create applications that could actually monitor the infrastructure that was in Building 16. An example here is the injector. And we created an application that can monitor each port. So every port we can monitor how much power is being delivered and also have control of the injector. So we could write programs that can enable and disable ports. So think about an end device that's connected and powered by an injector. We can actually remotely turn on and off devices when viable. So we also did this for the meters. So we have three meters for measuring solar demand and mains, and we were able to monitor them and create an application that could review all of the data that was coming back from the meters. All of this data we actually captured so that we could use it, and we stored it in a database. So we did this through our service, which is service aggregation for smart homes. And we were able to use this data to make analysis and review all of the data from the injector and for the meters, and review how much solar is being utilized and how much mains is being used. There was also a web application made, which can be used on a mobile phone. And this could review the whole system in Building 16. So we could see how much power is being generated, how much is using, and also review the injectors, so the end devices. So this was all created and custom applications made.
So as I mentioned in the first slide, we actually had to encompass the project to include distributed storage. So the only way to do this safely without electrocuting ourselves was to actually do it low voltage. So we chose to build a small USB charging box that could accept power over Ethernet and then charge a lithium battery pack, and then essentially transfer that power to USB so the staff at BRE could actually utilize the device. And the system had current sensors to actually monitor how much load was being provided, and so we can actually see who was using it. And wireless Zigbee protocol to actually send updates to our service. So these are the charging boxes we created. We created 4 of them and gave them to select staff, and they were charging their iPads, iPhones, Android devices all day long. Again, because we like making displays and programs, we made one for these boxes. So we were able to show the staff the charge status of each box and how much they were using to show their health.
So we also added some intelligence to the system. So if the batteries were continuously being charged by PV, that wouldn't be efficient. And also, it's not good practice to continuously charge batteries. So we thought we needed to add some control to the system. So what we did, as I mentioned earlier, we can enable and disable ports on the PoE injector. So we checked between the hours of 7 p.m. and 8 a.m. out of hours service, we actually disabled charging to the stations. So during that time, they would only use the internal battery of the battery pack. But we made sure beforehand that the packs were 50% charged so that staff didn't come in and find an empty battery pack. So this is adding intelligence to the system, and this was all done in real time by an intelligent system that was created. And this is the overall diagram of what was created. So we were able to see throughout this display what's actually going on. So the injector, what power is being provided, if we're actually providing power back to the grid, and also the charge level of each battery pack. So if you have a look, we can see which battery packs are full, which are low. This is all using the data that is sent to our web service, and we can see exactly what's going on with the system. So it was an overall display that showed all of this. And through our data, we're actually able to create graphs and show exactly how the staff have been using the boxes and also how much PV has been generated. And we were able to graph all of this by the collection of our data.
So to take the system a step further, we chose to create another application that would run on the PCs, which were also powered by Power Ethernet. The application overrides the power management features within Windows, the operating system. So we can either turn down the brightness of devices connected to the system, or if we found that there was not enough power being sent to the batteries, or someone was using a device somewhere else and it required power, if no one was using the PC, we could actually force the PC to either shut down or hibernate, depending on how much power was available. So we took it a step further than the actual project encompassed, and generated this application. So this is the diagram which we have now. It's essentially the same as before, but we have the inclusion of our cloud server, SASH, as well as the display PCs, which are in building 16, and the 4 extra distributed storage batteries, which are connected to the system. So what are the project outcomes? The outcome was a successful control system which actually charged the batteries fully when required, and to not leave the staff short-handed for lack of power. And it also led to future research, which Emilio and I are doing currently right now, in device identification for Emilio's, and for indoor passive location for Emilio's, and device identification for myself. So my thesis title is Smart Electrical Networks. So The PhD research is targeted at the energy sector and is focused on the identification of electrical devices and appliances at socket level. What does this mean? When you plug an appliance or device into a mains outlet, the system should be able to automatically detect what that device is and label it appropriately without any human input. So if you plug a fan or a light in, it should be able to tell you what those are automatically. It expands upon what Emilio talked about in the previous slide with the cloud service SASH and uses the energy monitoring to download to the database to store all this data. And combining these 2 points, we're able to open up new notions that actually aren't exploited currently to date. So I see 4 key benefits that the system could contribute to smarter buildings and future energy demands. The first is if we take the concept of actually identifying what a device is, we can grant a security profile or an energy policy to that device, either deciding whether it should be on or off. And using existing smart sockets, we can actually be able to control if the socket needs to be on or off in various rooms. So if someone is using energy in one room and they're not in another room and they left a light on, we can then turn that light off. The third point is to monitor the device electrical signatures. So if the device was to fail, you would actually get a notification. As the system is constantly uploading data to our cloud service, we can actually detect patterns in the actual electrical signature. And if it diminishes, then we're able to flag that warning. And the fourth is the categorization of the electrical usage by appliance type. So similar to that of what you have with your mobile phone plan, when you get your bill at the end of the month, it's itemized by how many calls you made, who you made them to, your text messages. This will be similar to the categories of lighting, kitchen appliances, white goods, and your other TVs or computers that you would be using. So how are you doing this? So as we are monitoring the electrical signature, I'll be capturing those characteristics of numerous appliances under load. And by load, I mean the actual current signature of it. I'll be using existing algorithms that haven't been applied to current energy policies and smart meters to actually be able to identify that. And as I mentioned before, I'll be using existing smart sockets that had been developed at the University of Hertfordshire and to actually aid in the identification and intelligence process. And the second is a self-learning algorithm which will detect if the system knows or doesn't know if appliance has been detected and then therefore learn new ones. So this is the current socket we have at the University of Hertfordshire. It's a non-intrusive load monitoring device. So it has 2 current sensors on for the socket in total, 1 on each side, a voltage sensor, and the similar components you would find in a typical smart socket. So what am I monitoring? So as I said, I was monitoring the current signature. So as we see in this diagram, this is the current waveform of a fan. It's an inductive device, so it doesn't start at the 0 degrees. And this is a light that was sampled. It's a normal sine wave, has some noise in it. This is a TV. Again, you can tell the characteristics of them are fairly different. And this is a PC. So these are the 4 current devices that the system has learned automatically and is able to differentiate between. you can see that the patterns, even though they are sine waves, they're very notable features that differ them. And this is the application dashboard that we're able to invoke and query the cloud database to actually see what the device is. So I wish I had a video to show you, but what this shows is the voltage sensor on the top right detecting a pure sine wave, and then time aligning the second and the third sensors for the current sensors to actually be in phase. And then it's able to detect what the appliances are. So if I zoom in, this isn't Photoshop, this is real. The device for the top is most likely a light, and the second one is a TV, and those are correct. So I've been working to actually better the algorithm to see if I can detect more devices, and that'll be in the next coming months. So this is the overall system architecture. So we have a number of smart sockets connected, which are able to extract the data and then broadcast that to over the internet to our cloud database. It invokes the service, and the algorithm detects whether it should learn or provide back a result. And then you can monitor this externally through a mobile device. And so my future work is, as I mentioned before, is to better the algorithm. It's fairly fast right now, but I would like it to be faster. And I would like to test this within homes in the coming months to get a real day-to-day usage to see if it actually can detect different devices around the home. And just recently, we've actually partnered with a university in China, and we're working with them to actually learn more devices over in Asia too. So our database is ever expanding. And that's it from me, and I'd like to pass it over to Emilio. So thank you very much.
Thank you. So the area of my research is indoor localization for smart buildings. So what do I mean by this? Where are people in buildings? This is an area that hasn't actually been accomplished. There's a lot of research in the area, but how can we find out where people are in buildings in a non-intrusive way? Because people don't like being watched in their own home. So we want to find a non-intrusive way of knowing where people are in buildings for various benefits. So, not only which room they're in, is it possible to know whereabouts in the room they are? Can we do this? That is my research. So, there can be numerous benefits for this, including safety, security, and the delivery of targeted localized services associated with smart buildings and smart cities of the future. So my key aims: develop a device-free indoor localization system where the user will not have any device on them, create a system based on sensor network interference, which I'll explain shortly, analyze, implement algorithms and develop custom hardware, and research into the possibility of detecting who someone is based on the pattern that occurs in the detection of them. So I'm going to go through each of these points now. So how do we usually localize ourselves or a device? It's using GPS. GPS is a great technology that's in many devices now, and it can navigate us. But what happens when you enter a car park or you go into a building? GPS signal is lost. This is because it requires a line of sight with satellites, which indoors you do not have. And the user must carry a device, otherwise you cannot be located. A self-sufficient system would not require any user involvement, so any user would be able to walk into any room and the house system would know where they are. So in current research, there are two main categories, active and passive. So when we hear active localization, this is localizing a person with a device. So with a device in a building, using installed wireless access points, for example, routers, there is research that can detect roughly where someone is. The problem with this is two key problems. The user must have a device. What if they put their phone down, they're no longer being tracked? So it's a big problem. Passive localization is the technology where you do not have a device. How can we do this? So the main benefits. This is used already in door localization. For example, shopping malls. A series of shopping centres now, actually. When you walk past a shop, if you have notifications, it will inform you you've walked past their shop and they'll send you a promotion. In a supermarket, when you walk past an aisle, they can send you notifications and say, you bought this item last week, it's cheaper this week, why not buy another one? This is technology that's actually happening. So there are many people that are after indoor localization, and it can be used for many things. More importantly, it could be used for healthcare and assisted living. For example, in care homes, it's very important to know where people are in rooms, and safety and security. How about in a fire? If we can find out where people are in buildings, it can be many benefits. But the aim is to make homes more adaptive to their occupants as well. So how is this done? So by using a series of small sensor nodes placed around a room, we can actually detect where they are based on signal interference. So when you have a transmitter and a receiver. Think of it as a laser beam. When you break that beam, you're actually causing interference. So there's been movement, there's been interference there. So if we have a series of transmissions around a room, we can detect which transmission beam has been broken, so therefore locating where they are. But this is not enough on its own. So a series of algorithms are being developed to actually overcome accuracy problems. So a series of software has been created. So we have a heat map visualization, which can actually see what area of the room someone is in. And to make this even more accurate, we are now training points within the center of the room as well, using training methods, so the room knows where someone is more accurately, not just near a node, so in the center of the room as well. All of this data is being stored for training data in our web service, and algorithms are being developed. So the hardware. Hardware has been custom designed in partnership with BRE and University of Hertfordshire, and they are very small sensor nodes with a microprocessor for processing and an RF chip for the actual radio transmission, where we are picking up interference. So this requires a lot of testing, because in radio frequency, things such as furniture, it can all interfere with radio. So a series of tests were done and calibration, so the system is calibrated to know furniture is in the room and don't take that into account. So testing so far has showed that we can actually detect where someone is in a room. So if you look at the top diagram, you have A, B, C. So we did a test that someone walks from A to C to B, and you can actually see every time it's at position A, the red and the blue actually dips each time. So we know exactly they're in that corner of the room, and again for B and again for C. So the signs are very good for detecting people. And also in motion, when someone's walking, we can actually see which side of the room they're walking on, because the pink is very prominent and the blue is not. So we know what side they are on. And results are showing us this. So there's also research into who someone is based on how much they interfere with the signal. So a larger person may interfere more, and we've actually proved this. So there's also research into this area, who someone is. And future work is train more fingerprinting examples, so the database becomes more full and the system will become more accurate. Develop algorithms more and test in different environments. Every environment is different, so we want to train the system in new environments. Thank you very much for your attention.